Math Analyzers. How are you? We are now in chapter 5. We're going to talk about imaginary and complex numbers. So, imaginary numbers, I know I kind of alluded to when you were a freshman in Algebra 1, but they do exist, even though they have the name, the unfortunate name, imaginary numbers, because they were thought of before we recognized that they existed. So, this imaginary name stuck. We call them complex numbers when we've got a real number and an imaginary number together being added or subtracted. And so that's what we're dealing with in this chapter. We're going to start today by talking about lesson 1, just looking at what imaginary numbers really are and why we call them that, but they do exist. Then we're going to add them, then we're going to multiply them, and have a review, have our quiz. Then we're going to rationalize them, 2 separate notes, 2 separate homeworks, but both deal with rationalizing the complex fractions. We're going to talk about something called the Argand diagram, which is really just a coordinate plane of real number and imaginary number together. And then we're going to talk about the absolute value of complex numbers. So we're going to basically see their distance. What's their distance in the Argand diagram? Okay. And this is, in these 2 lessons, kind of dealing with the same thing back and forth. One is visually and one is actually algebraically to deal with that distance part. Okay. So let's begin. Let's begin with lesson 1. So let's first start by talking about where we got imaginary numbers from. Again, they were thought of before they were found. So it's something along the lines of thinking about, well, 8 squared is 64 and negative 8 squared is 64. So I know what the square root of 64 is. It's either plus 8 or negative 8. But what if I have negative 64 under the radical? And you think about that and you think, well, I can't take the square root of a negative number. And you're right, you can't. There's not one number that multiplies together, not one integer that multiplies together, or that is the exact same number that gets me negative 64, because one of them would have to be negative. It's either got to be positive 8 and negative 8 that multiply together to give me 64, negative 64, or positive 8 and negative 8 that multiply together to give me negative 64, right? It's one of those 2. I can't get a negative by multiplying the same number by itself. So because of that, we kind of thought of these numbers with negatives under the radical, thought of their existence and called them imaginary before we realized these are numbers. They're just in a totally different number set than the real numbers, so the rational and the irrational. They're a new separate set, okay? And these are formed by having a negative number under the radical. So imaginary numbers are any of your numbers where there is no real roots to the quadratic equation, okay? So here's an example. If you have x squared plus 1 equals 0, you can subtract both sides to get this negative 1 over here. And of course, the opposite of squaring something is taking the square root. So that's what gets you your x alone. However, you've got this square root of negative 1 over here. And since we just discussed, we know we can't take the square root of a negative number that way. It doesn't result in a real number. What we call that is an imaginary number. Okay, this is still 2 answers. It's positive square root of negative 1 and negative square root of negative 1. But the new key for us here is that the square root of negative 1 is going to be equal to I, a little I, and usually cursive-ish, right? This is our imaginary unit, okay? This is our imaginary unit. So everything that I talk about with a little I is talking about having a negative 1 under the radical. Just like we can't leave any perfect squares under a radical, we actually can't leave a negative 1 under the radical. So we're going to bring that out in the form of a little I. Okay, that's what's going to come out. All right. We call this BI form. It looks like the word by, but it's actually BI, right? The prefix by, but it's BI. We call it BI form because the number in the front, that's your coefficient, and the I is your imaginary unit. That's your square root of -1. Okay? So I is that real number multiplicatively attached to an I. So, like I said before, completely separate number set. Here are all your real numbers. So we've talked about all these number sets. We've talked about how irrational numbers are a completely separate number set to those rationals, right? Well, now imaginary numbers are a completely separate set as well. Here's your real numbers. Here's your imaginary numbers. This makes up the entire big complex numbers set. So now that we're in Algebra 2, we can start using, we know how to use radicals now after Chapter 4, and now we're going to learn how to do those negative numbers under the radicals, so those i's, the imaginary numbers. That's what we're going to start looking at, okay, and start kind of looking at as a separate thing. And just like these cannot add together, neither can these. They're completely separate number sets, so they're separate terms when we look at them this way, which is why you have A plus BI. So two separate pieces. Okay, they're not going to combine further. That's kind of a cool thing. I love that diagram though. All right. So the first thing we have to do when talking about imaginary numbers is we have to simplify them. Okay, so just like you can simplify the square root of 48 by taking out any perfect squares, you can simplify the negative square root, the square root of -48 by taking out the imaginary unit and any perfect squares. So basically, it's just one more piece of the perfect square left over. Now there's one more piece that's an I. Okay. Once you take a -1 out of that negative number, the leftover is positive, and that's what you're dealing with the regular perfect square and leftover deal. Okay. We do attach the I. So when we take the square root of -1, we call it I. And we do attach this to any number coefficients. Okay. So by multiplication, and then that goes in front of any leftover radicals. Okay. This should be a 3, by the way. Change that to a 3. That's the leftover because we took the square root of -1. Okay. If the number under the radical is a perfect square when it's positive, then you just take its square root and attach an I to it. Okay. So there's 2 examples of that where this number, if positive, would have been a perfect square. So I take its square root and attach an I as my answer. Okay. So we're going to do a couple of examples. And what I did in these examples is I have a positive and a negative. So you can see how we comparatively simplify. Okay. Obviously, a perfect square, take its square root. So positive 36 is a perfect square, right? So I take its square root and I attach an I to it. Here, perfect square. What's the square root of 49? It's 7. 2 times 7 is 14 is my answer. Okay. Same thing here. I'm just going to write out my steps here so you can see it a little more. So my coefficient is 2. My radical -1 comes out. That's my I that's coming out. And then here, you're left with, once you take the negative out, you're left with a positive 49 under the other radical. Well, the square root of 49 is 7. The square root of -1 is I. And we're just going to multiply all these things together. 2 times 7 is 14, and 14 times I is 14I. Continuing. So here, it's positive 40 under here. Bring your coefficient over and divide it into perfect square and leftover. The biggest perfect square that divides evenly into 40 is 4. 40 divided by 4 is 10 for my leftover. What's the square root of 4? It's 2. Multiply those numbers on the outside together. -3 times 2 is -6. Radical 10 as my answer there. So now, okay, that's negative, right? Negative under here. we're just going to divide it into three radicals: perfect square, leftover, and the I, the imaginary one. And the I is always where the negative one goes. So you're taking that negative part out of the radical. Now you're left with radical 40. So it's the perfect square is 4 and the leftover is 10. Now take the square roots of what you can. So the square root of 4 is 2. The square root of negative 1 is I. So negative 3 times 2 times I is negative 6I. Radical 10 is the leftover. Look at that difference, okay? I'll do that other one at the bottom in red so you can see the difference here. So 8, biggest perfect square that divides evenly into it is 4. So radical 4, radical 2, right? 4 being the perfect square, 2 being the leftover. Square root of 4 is 2. So on the outside here, 5 times 2 is 10. Bring the leftover radical 2. So 10 radical 2 is my answer. Okay, here. Coefficient, perfect square, leftover, imaginary one. And the imaginary one is where the negative 1 goes. So now you're left with a positive 8. Well, 8 is evenly divisible by 4. 8 divided by 4 is 2. So where'd the negative go? It's right here in a negative 1 factor. So now we take the square root of 4, we get 2. We take the square root of negative 1, we get I. 5 times 2 times I is 10I. Radical 2 as the leftover. Okay, so look at those. There really isn't much of a difference in simplifying a positive number under the radical, simplifying a negative number under the radical. Okay, there's not much of a difference there at all. All right, I need to stop for 1 second so I can Zoom with virtual peeps, but I will get back to you guys in a moment. So hang tight. Where am I? There we go. Hang tight for me. I'll be seeing you guys in a sec. Ooh, don't want to trash it. All righty, guys. Sorry about that. I'm back. We'll get our screen back up. There we go. Move me back where I belong. And why do we use imaginary numbers, right? Hopefully you saw that as we were going through, but imaginary numbers are used for electrical currents. So when you get into, if and when you get into physics, right, you'll be doing electrical current work, and that's when you're going to use a lot of I's. So now we need to discuss with I something called the cyclical powers of I. And basically what this is going to do is it's just going to be, we can simplify I raised to certain powers, knowing that there are only 4 options of answers of I raised to a power. And those options are, they're all right up here. Okay. It's either I, that's I to the first power, or it's I squared as a negative 1. So notice an integer came out. Or it's I to the third gives me a negative I. Or it's I to the fourth gives me a positive 1. Notice again, an integer came out. So with the evens, integers comes out. With the odds, you're left with an I. Okay? So basically, it's up to us to be able to simplify an I raised to a power. So we never leave an I raised to a power. We simplify it down to an answer. And one of those answers is it's either I, negative 1, negative I, or positive 1. Okay? We call it cyclical because after I to the fourth, you get I to the fifth, right? Well, it restarts the pattern. After I to the eighth, you get I to the ninth, and it restarts the pattern again. So when simplifying powers of I, since it's a pattern of 4, find the closest multiple of 4 to that exponent. So in this case, 29 is my exponent. So the closest multiple of 4 is 28. Okay. This, since it's divisible by 4, is equal to 1. Okay. So that is equal to 1. Now this is your leftover, and what's the leftover equal to? Well, what I do is I write it out. So I to the first is I to the second is negative 1. I to the third is negative I. I to the fourth is positive 1. Okay. And so I to the first is what's left. That's equal to an I. The whole answer is I. That's how we're going to work these. And unfortunately, no, you cannot just plug that into the graphing calculator. Okay, so let's do some more examples. Even exponents and exponents that are multiples of 4 are going to have integer answers, either -1 or +1. If it is a multiple of 4, it's a +1. If it's an even number that's not a multiple of 4, then it's a -1. So that's kind of the easiest ones to think about. It's the odd ones that are a little bit more challenging to think about. So let me look at them. Oh yeah, in the imaginary, in this entire chapter, I've laced in some real nice little imaginary numbers, comics and jokes and puns. So look forward to those through your lessons, right? So look at the power, find the closest multiple of 4 without going over. So closest multiple of 4 without going over to 7 is 4. So I to the fourth goes here, and then the leftover is I cubed. Okay? So this cancels out to a 1. I cubed is equal to negative I. That's your final answer. Okay? If it's an even number, check to see if it's divisible by 4. 38 is not. So the closest multiple of 4 is 36. That's going to cancel out. What's the leftover? 38 minus 36 is 2. I squared is equal to -1. That's your final answer. Again, 78. 78 is not divisible by 4, but the closest one that is 76. And then, of course, the leftover is 2. So this cancels to a 1, and -1 is your final answer. I squared is -1. Okay, multiply these together, which really means add the exponents, you get 27. Okay, what's the closest multiple of 4 to 27 without going over? That's 24. And 27 minus 24 is I cubed. So this cancels to a 1. I cubed is equal to -1. 20 is a multiple of 4. So this is equal to 1. If your exponent is a multiple of 4, it's equal to 1, your answer. 23, closest multiple of 4 without going over is 20. So I to the 20th times I to the third. I to the 20th cancels to a 1. I to the third is -I. 53, closest multiple of 4 is 54. 52. 52 divided by 4 is 13. So yes, there we are. And then an I to the first is left over, right? This cancels out to a 1. I to the first is just an I. That's your answer. Now this one is interesting because they're adding, they're two separate pieces. So find this one first, which is -I, and then find this one second, which we're going to put it in parentheses. Closest multiple of 4 without going over is 88, and then an I to the first left over. So this is really just an I. So I'm going to do this -I plus +I. And think of those as like terms, and when they add up, you get 0. That's the whole next lesson. Aw, cute. He has an imaginary friend. Ha, get it? All right. Cyclical powers of I have a tendency to be tougher on people. So just real quick, I'm going to go to the homework. Okay. So second page of the homework is where the cyclical powers of I questions are. Okay. Again, look for the closest multiple of 4 without going over. Divide it into that piece and then subtract in the exponents. 35 minus 32 is 3. This cancels to a 1. I to the third is -I. And if you don't have that part memorized, just right over here to the side of your paper on your homework, write them down. So I to the first is I to the second is -1. I to the third is I to the fourth is 1. So that's the powers that keep cycling back. Okay, so since it's a power of 4 that then recycles, starting with I and then -1 and then -I and then 1, that's why we look for the closest multiple of 4 without going over. And that's what we cancel out. And whatever is that left over, that's what we compare it to. Okay, so just try that as you're going through. Should be a little bit easier if you do it that way. But if you need me for it, just ask. I am more than happy to help you with these. I know eyes are brand spanking new to us. So good luck, guys. Let me know what you need. And I shall be seeing you real soon. Have fun with all our imaginaries, our eyes. Our complex numbers are just going to be a blast. All right, I'll be seeing you guys.